Hello and welcome to CMOS RF integrated circuits. Today we are going to continue from where we left off. In the previous class we discussed in detail phase noise properties, rather we just did a noise analysis. The noise, it so happens that that noise is called phase noise because if you are expecting a square wave, there is no noise in the amplitude. You can cut out the noise in the amplitude very easily. So, all that remains is the phase noise. So, that is why I am calling it that we did a phase noise analysis. We did not really do a phase noise analysis as such. What we did was a general noise analysis, and I showed you that instead of getting an impulse in the spectrum, you get an impulse with a skirt around it, and that skirt is because of phase noise. So, how it is quantified? So, this is what I have, and how it is quantified is you say that with respect to the carrier at an offset frequency from the carrier of so much, at so much offset frequency, I have got so many dBs less of noise. So, it is called so many dBc, dB with respect to the carrier at an offset frequency of so much from the center frequency, from the carrier frequency. So, that is how we quantify the phase noise in an oscillator. All right. So, today we are going to talk about other oscillator topologies. So far we have just stuck to the one, it is a very popular oscillator topology as such. So, that is why we did a very detailed analysis of it. So, this is what we have done so far. So, this is a negative resistance based oscillator. So, I have got a tank and I have got a negative resistor to compensate for the tank loss. Basically the loss is in the inductor. So, to compensate for that I have built a negative resistor, and when the negative resistance, when the negative conductance is more than the positive conductance of the tank, then oscillations win and my poles go into the right half plane of the right half side of the S plane, which means that I get oscillations. So, this is what we have done so far. Oscillators, typically every time a person created an oscillator, they add a name to it. So, there is Colpitt's oscillator, there is Hartley's oscillator, there is the Clapp oscillator, so on and so forth, lot of different, there is the Pierce oscillator, lot of oscillator topologies are available. Most popular, besides the one that we have already studied, is the Colpitt's oscillator. That is also, all of these topologies are based on the tank circuit. So, let us briefly take a look at the Colpitt's oscillator. So, we need a tank. Tank means that wherever you have an inductor, the inductor is really not a pure inductor. So, I am going to model the inductor as an inductor in shunt with a resistance. Now, note this resistor is not intentional. This is something that has come as a result of placing the inductor over there, eddy current losses, series wire losses, etc., copper losses, right. And usually this is my tank circuit. Now, what I am going to do is, instead of having this, I am going to break this capacitor into two capacitors in series, all right, and I am going to take out the voltage from the middle and feed it back. So, this is more or less the topology of a Colpitts oscillator. So, I have got a tank and I take out a fraction of the voltage on the capacitor, feed it back to the source. Now, what does this do? So, as far as the small signal voltage is concerned, so in the small signal sense, let me redraw my circuit in the small signal sense. In the small signal sense, this bias current is an open circuit. The bias voltage is a ground potential. So, if I redraw my circuit, this is what I have got, right. Or in other words, if I try to draw it a little more, if I reorganize my drawing, it is going to look like this. Right, this is the common gate structure. This is the common gate structure. Remember? You put your input here and you see your output there. This is the common gate structure. The gain of, there is the gain of the common gate amplifier. The common gate amplifier has a gain of positive GM times, let us not call this R, let us call this Z. This is the gain of the common gate amplifier, and the input resistance of the common gate amplifier is going to be what? Is going to be RDS plus Z divided by 1 plus GM RDS. If Z is small enough, let us say if Z is 0, then the input resistance, input impedance is approximately equal to 1 by GM, okay, if Z is small. All right. So, that is what I have got. Okay, so, this is a feedback circuit. There is, so the voltage here, I am sorry, this is sensing a voltage. So, the voltage here at this point is amplified by a factor, the amplification is GM times Z parallel RDS and is put over here. Now, notice that the gain of the amplifier is positive, which makes it a positive feedback circuit, right. So, this is your Colpitts oscillator. So, when the gain is positive, when you have a positive feedback system, a positive feedback system means that you have got some sort of negative resistance going on there, right, and that will make your system, entire system oscillate, or it will place the poles on the right half side of the S plane. So, that is basically the idea over here. You can do a detailed analysis, it is not terribly difficult to do a detailed analysis of the Colpitts oscillator, and you can show that the frequency it will oscillate at is basically the tank frequency. So, this is my L and the C is series combination of C1 and C2. So, that is the typical frequency of oscillation, that is the tank, right, L, and you split up the capacitor into 2 pieces. So, that is why I am saying series combination of C1 and C2. So, the tank frequency of oscillation is right, and this is when the positive feedback is enough to precisely cancel the resistor that you have got, the damping resistor that you have got. All right. So, this is a Colpitt's oscillator. A Hartley oscillator is very similar, very similar, and instead of having a capacitive divider for the feedback, we will have an inductive divider, that is all, right. So, that is your Hartley oscillator. So, now I am not going to show the biasing over here, it is not terribly easy to see what is going on with the biasing, because if I put a current source to bias over here, all that current is going to go through this, nothing is going to go through the MOSFET. So, that is not going to be a correct biasing strategy. So, I have got to put some sort of VGS over here, typically that means that you could do potentially something like this. Right. And once again this particular R is not something intentional, this came as a result of problems with your circuit. So, this is the Hartley oscillator, it is just a variation. There are a couple of more such oscillators, there is the Pierce oscillator, clap oscillator, etc., a lot of different oscillator topologies exist in the books. More or less they are all based on the same principle. You sense the oscillation and you create a positive feedback and feed it back to create more oscillations. This is basically the idea. All of these are tuned oscillators and the outcome is typically, hopefully, a square wave. So, that is the target. So, all of these kind of achieve that target, you get a square wave. Okay. Now, another very popular oscillator is the ring oscillator. It is a very popular oscillator, especially in the digital world. A lot of clocks on CPUs are generated sometimes through ring oscillators. So, a ring oscillator is something very straightforward. I can design a CMOS inverter. CMOS inverter is something like this. This is your CMOS inverter. So, I can design a CMOS inverter and I can put an odd number of these inverters in cascade odd greater than 1, and feedback. So, this is a ring oscillator, it is a 3-stage ring oscillator. Similarly, you can make a 5-stage ring oscillator, 7-stage ring oscillator, etcetera, etcetera. You can convert these inverters into differential inverters, and you might as well do it differentially, in which case you need not have 3 stages, but that is secondary as far as we are concerned. All right. So, this is basically the idea. So, let us say that each gate has a delay of d, each inverter has a delay of d. Where is this delay coming from? This delay is coming from the amount of current that the inverter uses up and the load capacitance. The load capacitance is the gate capacitance of the next stage. So, that is where this delay is coming from. So, it takes some time for the current to charge up the output. All right. So, that is basically where the delay is coming from. Let us say each of these inverters has a delay of d, then if this is a 1, then after a delay of d this becomes a 0, after a delay of 2d this becomes a 1, after a delay of 3d this again becomes a 0, which is the same net. Right. So, if this particular wire is a 1, after a delay of 3d it goes back to 0, after another 3d it will again become a 1. So, the net period is 6 times d, which means that the oscillation frequency is going to be 1 by 60. So, this is trivially simple to analyze. If you can figure out what this d, the value of d is, you are done, right. What is going to be the value of d? The load capacitance is the gate capacitance of the next stage, which is basically CGS of the next stage. It is also the drain to body capacitance of the inverter itself. So, it is something like this. Right. So, this is the load capacitance that each inverter sees. Each inverter sees the same load capacitance. Now, if you think about it, each inverter is seeing this load capacitance and the amount of current it is drawing from the power supply, the amount of current is VGS, VGS is VDD minus VT the whole squared. Something of this magnitude. Of course, this is when the device is on, it is not really correct. The device is, I am sorry, this is when the device is in saturation. The device is not going to be in saturation most of the time, it is going to be in the linear region, in which case you have to modify this equation, and hence this current thing is not really correct, but to first order you can see that if I increase VDD the current is going to increase. So, the current is proportional to V, not going to say proportional over here, the current increases when I increase VDD. Also when W by L increases, I increases. Okay. Cox increases, I increases, which basically means that if I make the thickness of the oxide layer smaller, then I will increase, area larger, I will no, this is per unit area. Mu the mobility, if I increase the mobility, then also I will increase, etcetera, etcetera. You can figure this out, and so that is the current. This current has to charge a capacitor, and that is what you have over there. You get a delay. Right. So, this is the analysis from this perspective. If we think of doing a small signal analysis, let us think of, let us conceive of a small signal analysis. It is not really correct to do a small signal analysis, because the signals are large. So, you can't possibly do a small signal analysis, but then again we did the same thing for earlier setups, right, where the signal was large, we still did a small signal analysis and kind of got a feel for what is going on. So, let us do the same, let us try to get a feel for what is going on. Each stage over here okay, let us draw each stage is Gm times Vgs. Here Gm is really the Gm of the NMOS plus the Gm of the PMOS. In shunt with RDS, RDS is really RDS of the NMOS in shunt with RDS of the PMOS. Okay. What about capacitors? As far as capacitors are concerned, I have got a gate to drain capacitance. This gate to drain capacitance is really the sum of the gate to drain capacitance of the NMOS and the PMOS. I have got a gate to source capacitance, which is again the sum of the gate to source capacitance of the NMOS and the PMOS. I have got a drain to body capacitance, which is again the sum of the drain to body capacitance of the NMOS and the PMOS. Source to body is irrelevant because source and body are at the same potential, right. So, this is each stage, and you would like to repeat these stages. all right. So, this is what you have got. You have got a complicated network, it is not really that complicated. You can simplify this to this. Right. Now, these gate to drain capacitors pose some kind of a problem, because they are between two terminals and not with respect to ground. Typically, you can break this, you can conceive of breaking this using Miller's approximation, and if I break the gate to drain capacitance using Miller's approximation, then it breaks up into A times, where A is the gain of each stage, A times CGD on one side and CGD on the other side. So, each side is seeing a CGD, each node is seeing A times CGD, each node is also seeing 1 times CGD. So, each node is seeing approximately 1 plus A times CGD, right. So, you can simplify this using Miller. You can simplify this by just having one resistor and one capacitor. At each node. So, what I have done is I have broken up the gate to drain capacitors. Each capacitor on each node is really CGS plus CGD times 1 plus A is GM times RDS. So, this is each capacitor that you have got. Let us say that this is a C and each resistor is RDS, right. Let us say we call it R. All right. So, this is what I have got, and of course, GM, all of these different components are really the total between the NMOS and the PMOS taken together. This analysis is for a small signal when both the devices are active at any given bias point. This is the analysis. All right. So, this is what I have. Each stage is therefore going to contribute a pole. And there is going to be gain associated with each stage. So, if I have got V 1, then V 2 is equal to G m times V 1, this is the current, times the impedance. The impedance is really R parallel 1 by j omega c. Okay. If I have got V 2, then V 3 is the same factor times V 2, and if I have got V 3, then V 1 is the same factor times V 1. So, the loop gain of the system is G m cubed times R parallel 1 by j omega c whole cubed. This is the loop gain, negative. I am sorry, there was a minus sign that I missed out. All right. So, this is my loop gain, and I think I would really like to convert this R parallel 1 by S c. R parallel 1 by S c is R by S c by R plus 1 by S c, which happens to be equal to R by 1 plus S c R. Okay. Now, when you do your analysis, whatever you want to find out some parameter, right, your expression is going to have 1 plus the loop gain, I am sorry, 1 minus the loop gain in the denominator. So, something you are trying to find out, your denominator will have 1 minus loop gain. Now, this loop gain is really G m cubed by G m cubed times R cubed divided by 1 plus S C R the whole cubed. Right. And really what this means is that you have got something times 1 plus S C R the whole cubed divided by 1 plus S C R the whole cubed plus G m cubed R cubed. So, your denominator contains this as its denominator polynomial. Now, if this is the denominator polynomial, then the poles are the roots of the denominator polynomial. Now, it is hard to find out the roots of this cubic equation. It is quite hard to find out the roots, but if you do your analysis, you will find that a pair of roots fall in the right half plane. Pair of complex conjugate roots will be there in the right half plane. So, that is basically the idea of this. If I had just two inverters in series with feedback, then first of all I would not be getting the negative sign, I would be getting a positive sign here. So, that is a problem. Okay. So, it is not going to create negative feedback, it will work as a latch. It is going to create some positive feedback at DC, it will work as a latch. All right. So, this is basically the analysis of the small signal model of a ring oscillator. Now, why I did this was to hint at the fact that suppose there is equilibrium, suppose you have designed your inverter very carefully, you have designed your inverter very carefully, you have chosen the widths and lengths of the PMOS and NMOS devices very carefully, such that if VDD by 2 is the input, then VDD by 2 is the output precisely. Okay. Now, I put 2 more such inverters. The second inverter has an input of VDD by 2. So, its output is going to be VDD by 2. The third inverter has its input as VDD by 2. So, its output is also going to be VDD by 2, and I feed it back. Where is the oscillation? There is no oscillation if you think of it this way. But wait, this is the exact situation under which we did our pole 0 etc. analysis. Right? This is the precise situation, it's beautifully biased, all the nodes are at VDD by 2. So, I use small signal models, okay. All the devices are active etc. I use my small signal model and I see that this is going to be the denominator polynomial of the expression for any particular voltage or current. Now, if that is the denominator polynomial, then there are some roots on the right half plane, which means that whatever that quantity is, it is going to start growing exponentially and with sinusoidal voltages, it is going to grow exponentially, and if it starts growing exponentially, then it is caught off balance. So, this VDD by 2 is no longer going to remain, because something has changed, perfectly balanced, something starts moving away because of the poles being on the right half plane, and as a result it is no longer going to be at perfect balance everywhere. So, this is basically the idea. This is why we did the pole 0 analysis, to prove that this thing is indeed going to oscillate. Did not really complete it, because I can't find out the poles of a cubic, the roots of a cubic by hand, but I gave you the way. All right. If Gm times R is large, Gm times R is a number like 20, right. So, keep that noted as part of this discussion. What about the phase noise? As far as the phase noise is concerned, we did similar small signal analysis for the tank circuit, remember, and if I do a phase noise analysis of this particular oscillator, of the ring oscillator, what you are going to find is this. This is going to be my scenario, and let us say that I am going to take the output from here. Now, the way we do this is we take each noise source at a time and then work it out. Each noise source we are going to take at a time and then find out the output because of each noise source and then add them up, add the mean squares of all of these noises together, and that will be the mean squared noise voltage, the total mean squared noise voltage at the output. That is how we are going to do our business. All right. Now, what you can see over here is that I n 1 squared is going to go through some sort of a low pass filter, RC low pass filter, to create V 2. That V 2 is further going to go through another RC low pass filter to create V 3. That V 3 is going to go through another RC low pass filter to create V 1, right. That V 1 of course is being fed back. Now, if this is the situation, then what do you expect the noise voltage spectrum to look like at the output qualitatively? If I have noise at DC, let us say I n is a DC noise current. So, that will create a V 2, that V 2 is going to create an amplified V 3, that V 3 is going to create an amplified V 1, right. The net result is going to be that I am going to get some noise at DC. Of course, at the desired frequency of oscillation, the noise is going to shoot up. At the frequency of oscillation, the noise is going to shoot up, but what I want to suggest over here is that if you do a small signal analysis of the noise, you are going to find out that there is going to be noise at DC. It is some sort of a low pass filter, okay, with a cutoff frequency of 1 by RC. So, noise will be there all over from DC to 1 by RC, to a frequency 1 by RC or so. So, all of this is called phase noise. Now, compare this to what you got before. Compare this to what you got before. We did a more detailed analysis, of course. Right now, I hardly did any analysis. I just said qualitatively it looks like noise will be there at DC. Over here there is no noise at DC, it is clean at DC. We saw that the noise at DC is perfectly equal to 0. This was my equation for the noise. Okay. We proved that noise at DC was perfectly equal to 0, and that is because of the band pass nature of the LC circuit. So, the LC circuit is a band pass circuit, right, LC filter, it is a band pass filter. So, the band pass nature of the LC circuit allows noise through at 1 by square root of LC, it does not allow noise at any other frequency. Over here qualitatively, if you look at it, this is not an LC circuit, this is an RC circuit that you are using. RC circuit does not have band pass characteristics, it has low pass characteristics. So, noise will be allowed right through from frequencies starting at DC. Now, of course, if you take into account only thermal noise, this is how the spectrum is going to look like. If you take into account effects of flicker noise, 1 by f noise, then this is actually going to grow at DC. This is also going to appear as phase noise. So, everything over here, all the noise is phase noise, it cannot possibly be amplitude noise, the amplitude is a square wave, right. So, this entire all the noise that you are seeing is really expressed at the output as phase noise or jitter, uncertainty in the period of the oscillation. So, jitter and phase noise are basically the same thing, you can mathematically correlate one to the other, and you can see that for a ring oscillator you get huge quantities of jitter because of 1 by f noise, because of the very low pass characteristics of the oscillator. Whereas, as far as an LC circuit is concerned, 1 by f noise is of no concern, because at DC noise is completely filtered out. Okay. So, low frequency noise is filtered out. 1 by f noise does get modulated because of non-linearities, but that is a different mechanism altogether. So, you will see effects of 1 by f noise even in LC oscillators, but not to the extent that you see in ring oscillators. Okay. So, we want to make a system for a cell phone, accurate frequency is of great importance to us. We want to compete with atomic clocks. We definitely do not want large quantities of jitter. So, this is the ring oscillator systematically, because of the very nature of the circuit, the low pass nature of the circuit, allows noise at low frequencies. So, that is bad. We do not want to make ring oscillators when we want to design for a cell phone, where we want to compete with atomic clocks, crystal oscillators, quartz crystals, right. So, this leads us to the design choice of LC oscillators. Almost invariably you will see LC oscillators at the heart of oscillators in circuits for radios, circuits for cell phones. So, inductor is a costly component, but it has got to be used. Right. So, with this as our background, we have studied phase noise mechanisms for the generic LC tank oscillator with a negative resistor. It is a very generic oscillator, actually it is so easy to make and so easy to design and understand that it is very popular. There also exist the Colpitts oscillator, the Hartley oscillator. Difference is that both of these, the other techniques, the named oscillators use one device. So, it is actually quite neat if you want to make these oscillators using discrete devices. I do not have two devices to spare, I would rather make it with one device. So, Colpitts oscillator, Hartley oscillator, these are older oscillators when devices were of great demand, were of high price. And all of these are popular oscillator topologies. They all use some sort of feedback, some sort of positive feedback mechanism at the chosen frequency of oscillation. All right. So, with this we are going to move on to the next topic. The next topic, the next module rather, okay. So, let me first motivate frequency synthesis for you. In a radio system, in a wireless system, there are two things. One is you need a pure frequency. Okay. Jitter in the time period of the oscillation is bad. Phase noise is bad, phase noise is the same as jitter. You do not want to have any phase noise in your system. That is number one. Number two, you want to make an oscillator which when demanded can move around. So, let us take an example. You switch on your cell phone, the oscillator tunes to a particular frequency which everyone knows is the pilot frequency, where the base station will send its information, instructions, initial instructions, random access channel, right. So, oscillator will tune to the random access channel first. Then the base station will instruct the cell phone to tune to a certain frequency. Immediately the oscillator will have to tune to that certain frequency for specific instructions. Then the base station will tell the cell phone that look, you have to go to this particular frequency because a certain other user has switched on his cell phone in your neighborhood. You do not want to interfere with him. So, immediately you switch channels. Okay. So, basically the idea is you keep on switching channels from time to time, and you have to do this at a very rapid rate. Okay. I am going to call this agility. Your oscillator has to be agile, it has to be able to move around as rapidly as demanded by the base station. The next thing is your oscillator has to be accurate. What do I mean by accurate? If the base station tells you go to 1 gigahertz, you have to go to 1 gigahertz precisely. You can't go to 1 gigahertz plus 2 hertz, or you can't go to 1 gigahertz plus 1 kilohertz, that is not acceptable. So, this is the third thing. So, there are these three components. You need a pure frequency, but of course, phase noise is no good. You need to be able to be agile, and the third thing is you need to be accurate when you talk about what is the precise frequency that you are oscillating at. Now, we all know that as far as a pure frequency is concerned, if I try to build something on chip, then the inductor will have losses, lossy inductor, low Q. The quality factor of the inductor is like 5, maybe 10 if you have done a very good job, 10. So, as a result, you will have a lot of phase noise. On the other hand, a quartz crystal can give you a jitter of 10 parts per million. That is very, very good in terms of phase noise. It is a very clean frequency. The next thing is, as far as accuracy is concerned, a quartz crystal can be treated as a reference. If the manufacturer of the quartz crystal tells you this crystal oscillates at 26.001 megahertz, it oscillates precisely at 26.001 megahertz. It does not oscillate at 26.001 megahertz plus 5 hertz. Okay. So, as far as a pure frequency and accuracy go, quartz crystals are unbeatable. As far as agility goes, your voltage controlled oscillator is definitely agile. It is just that you have no idea of what that precise frequency is. Also, you have very little control over the phase noise in your system. So, we need a mechanism to combine the quartz crystal, which is external, with the VCO on chip and get the best of both worlds. We want agility, but at the same time we want a pure frequency, we want very low phase noise, and we want great accuracy. We can't tolerate random frequency. Okay. So, with this in the background, we are going to stop, and we will continue with this discussion on frequency synthesis in the next class. Okay. Thank you.